This is our fourth session that we are having this year. We're very glad that you will be able to come here and now spend some time with us. First off, this is not a training class. Basically, it's just that we have some thoughts and we want to have an active discussion so that we learn about you guys, what you are doing, and what we have done. Basically, I have within my team Lijesh and Krishna. All three of us work for Neiman Marcus. We have our office is in Irving. So, if you can introduce yourselves, tell us where you work, what you are doing, anything with related to machine learning, we'll be eager to learn. Ready to start?
Yes. Hi, my name is Soham. I'm working as a data analyst with IMCS group. So I'm using SQL and Python. But currently I'm learning about machine learning, artificial intelligence, and some algorithms. So I'm planning to jump into data science. So that's why I'm learning machine learning, Python, and some statistical algorithms.
Awesome.
Thank you.
Hi, I'm Magnus. I work for Arthur Connected. I work as a tech lead in a microservice project. Our product doesn't use machine learning or AI, but some others are. I'm interested to start learning more.
Okay. Great.
Hi, I'm Julie Hall. I have a web development company, and I'm just interested in learning different things. One is artificial intelligence and machine learning. And we're interested in the speech part of this.
Sure. Yeah, we'll try to cover some parts of it. When our focus mainly today is deep networks, but we'll try to see if we can get some time allocated for that. Yes.
Hi everyone, this is Manoj. I'm manager in Infosys. I'm working for Toyota client. We have a data warehouse legacy platform which planning to transform to big data and ML and all those the new generation platform. And so I've done basic courses on ML and all. I have some idea, but I'm clearly just interact and stuff. Thanks.
Great. Thanks for joining.
Hi, my name is Mayank. Currently, I'm working for the West Fargo right now. So I'm working as a data analyst. We are mostly supporting the regulatory reporting and the engineering journey. So yeah, I'm just trying to learn machine learning and deep learning. So.
Great.
Oh, my name is Kip Sara. I work for GM.
Okay.
I mainly do NLP type of stuff.
Oh, nice.
Yeah, my name is Ashwin. I'm a brand new graduate from University of Northern Kentucky, and I'm in the data science.
Oh, very nice. Very nice.
Hi guys, my name is Andrew Kelly. I started the Blacks Technology meetup group. We hosted a machine learning meetup with Redfin, not too far from here. Looking to get more out of Anaconda 3.6 than my current hobby level. Kind of just messing around.
Awesome. Okay, if you didn't realize there is food here, so feel free to grab a bite. Now let me introduce Lijesh, who will do most of the talking today, and then feel free to ask questions. We will jump in wherever we can. Thank you.
Okay. I think the few months back, so our last session was 4 months back, and we had a good session back then. So we had called one of our guest speakers, who was a CPO of NBC Universal, and he was here. He talked through the intuition about vector subspaces, right? People, I think you guys, since you are in data science, you understand. Yeah, in terms of what area did he speak to, right? So I think what we decided that the content for today, knowing the kind of audience we are getting, we'll keep it to very basics, right? Kind of provide an intuition of what machine learning is, right? Of course, feel free to ask questions and we can have a robust discussion. I think like Raj was saying, right? One of the reasons we started hosting this meetup session is to basically kind of create a forum of machine learning, people like yourself. Looks like you also have a meetup group pretty close by, right? So we wanted people who are interested to come in and we kind of have this, work together session. So that's our hope. So let me jump into neural network, right? So I realize that many of you here has probably not worked on traditional machine learning algorithms ever, right? So there's traditional machine learning algorithms, and then there is deep learning, right? So the focus of today's, talk essentially is to talk to the deep learning concepts, right? So traditional, when I talk about traditional machine learning, right? The traditional machine learning. So can someone? We try to make it more interactive. Can someone help me understand how is machine learning different than like the way we used to build applications, or way we used to build any implementation? How is machine learning different?
So I've been told that in machine learning, you teach the machine, and in deep learning, the machine teaches itself. I don't know if that's right.
And okay, so in general, machine learning is in action, right? Sorry about it. So before we get into difference between machine learning and deep learning, I was kind of wanting to know, when you think about machine learning, what do you think? What is machine learning?
As per my understanding, machine will predict how the system will work in the future, whatever the business criteria will work on in the future.
Okay.
So mostly it's the future prediction.
Okay.
In my opinion, like machine trying to learn some rules based on the data it's fed to.
Okay. Yeah, exactly. Right. So in traditional application building, we would put in the rules in our program, and our program would basically, assess input based on our rules and, put out an output, right? The way machine learning is different is, for machine learning, all it needs is data, right? It looks at the data, it learns from that data. You provide that input, it kind of tries to match to the data distribution, right? And kind of puts out the output. As you can imagine, in traditional programming, you would be limited by the extent of logic which you can think beforehand, versus machine learning, which is learning from the data. So as you throw in more data, new data, it's able to learn itself and change. So that's where the strength of machine learning comes. Right? Now going to what you said. So what's the difference between a traditional machine learning versus deep learning, right? So traditional machine learning, when you think about, so I listed a few differences. But at the heart of it, the traditional machine learning is basically, trying to look at the data and trying to understand what it means. So it's trying to interpret your rules, your logic based out of data. Right? When you think about deep learning, the way deep learning is different is instead of learning the rules, it is trying to learn the representation of the data itself. Right? So that's one of the primary differences in terms of its operation. Right? Another difference is traditional machine learning is very shallow, right? Unlike deep learning. And we'll talk about it, I'm sure. Right now, the intuition, I'm not able to probably give it to you, but as we talk to you, you will realize what deep learning brings to the table. deep learning is, has several layers, and every layer kind of has a specific task, right, which it does for you, right? So if you were to imagine a crumpled paper, right, as you open that crumpled paper, right, deep learning in a lot of ways works that way, unwraps or unravels one layer at a time, and as we go through more layers, it kind of builds a composite representation of the data. The third element, which feature engineering, right? Does anyone know what feature engineering is? Go ahead, sir.
Yeah, trying to create numerical data from existing data. So anyway, re-engineering, like log transformation, you can transform text into numbers, all those types of things.
Right.
So that the machine will need numbers to look at them. So if you have text images, you have to convert them into numbers.
Yeah. So to put it out simply, feature engineering is basically preparing your data in a way that your algorithm can understand. And this is one of the major differences when you think about a traditional machine learning versus deep learning. Because in traditional machine learning, you have to look at the data and you have to kind of understand what data is relevant to the output which we are seeing, right? And kind of feed only those data into the model for it to come out with a prediction. Unlike deep learning, in the case of deep learning, all you have to do is throw data at it for most part. It is able to look at the data, it is able to learn what data is really relevant for my output versus what is not, and it kind of is not tightly coupled with the feature engineering. Because as you can imagine, feature engineering is largely on manual input. Someone has to look at it, someone has to prep the data, so it's prone for manual error. So in that sense, deep learning is really brings a lot of benefit. And of course, the last three, the hungry for data, as I said, deep learning learns representation from data. So as much as you can throw data into it, the better it becomes. Unlike traditional machine learning, in traditional machine learning, you can imagine, like a linear regression or log regression or a random forest, and there are simply so many algorithms, right? Those are shallow networks. At certain level, when you throw data to it, if you throw more data at it, it doesn't really learn. Unlike deep learning, where it can learn from additional data. The GPU needs, needless to mention, as you throw in more data, it needs more computation power. So of course, deep learning needs more GPU and has higher accuracy than traditional learning. Yeah. Any questions? Go ahead.
So is it similar to say that machine learning is good at handling multivariate equations, whereas deep learning is better at handling multivariate arrays?
State that question again.
Is sort of machine learning good at handling multivariate equations and deep learning better at handling multivariate arrays?
How would you describe a multivariate array?
Just like a 2x2 or an n by n
Matrix.
No. In either case, deep learning will do better than single layer shallow learning.
Gotcha.
If you think about shallow learning, right? Like I said, shallow learning is pretty much based on is trying to derive rules rather than learn representation of data, right? So whether it's multivariate array or equations doesn't matter, right? There is not enough depth in the model to learn behaviors from the data. Is the
one
question? Yeah, go
just
ahead.
one question. So when we say traditional machine learning, most of the time input will be like text or maybe flat file and things like that. Right? But in deep learning will be a visual, audio, and all. Can we say there is a difference between these two in terms of features, type of features?
In a way, yes, because I'm careful when I say that, right? So like I said, for deep learning, shallow learning, you have to prep up the data before you push into model. So if it's were text, like the gentleman there said, you have to think about how to do representation in numbers and then feed into a shallow network. Unlike deep learning, where you can throw content at it, like in this case, text can be directly fed into deep learning, and it can basically get the embedding representation of the text. So it has that capability. So in that sense, it is different. But so the way machine learning used to work before deep learning was there were stacks of individual shallow learning traditional algorithms, which is some input, output, and then you kind of move that output to a different shallow learning algorithm. So they would train and stack them differently. Anyways, not getting too much in shallow learning because we want to move towards deep learning. That's where which we wanted to talk about today. So does anyone know about ImageNet data? So ImageNet data was so ImageNet actually really sparked a lot of changes. In fact, that's when deep learning really took off, right? So while the data scientists and machine learning pioneers were kind of focused on building models, there happens to be a lady, her name is Lee, and I think she teaches right now in Stanford. So her motto was, let me go and get as much data as I can, right? And that's where she wanted to build a database of images with classifications, right? So just so you know, right, for any model, right, you have to basically feed it data, right? I have to feed it, say suppose I wanted to recognize cat from the other animals, I have to feed it images of cat, say, hey, this is cat, and I have to feed image of dog and the other animal and say to it, hey, this is not a cat, right? So you have to really feed data into it. And prior to ImageNet, there was not such a huge database of images. So she went on a mission where she wanted to create this huge data set of images. And right now, I think it's close to 14 million images with more than 20,000 categories. It's really a huge set. And how that helped, because now models got access to this huge data set. So if you see on the right hand side, I think that is not very clear here. If you look at the accuracy percentage, in 2012 there was a huge drop in error. I don't know, it's probably not visible on the sheet here. Probably you're blocking it.
Sorry.
So that's when ImageNet was pushed out, and AlexNet, which happened to be the model for identifying different classes, I think its error rate dropped to less than 80% in 2012 because of ImageNet images. And since then, machine learning has really taken off. That's just a little bit of history. Okay. Yeah, briefly talk about this, and then probably we'll get into deep learning. So, so if you look at the chart there, or the history of machine learning, you can see machine learning had been out there since a long time. Right? In fact, what I'm talking about is pretty much between 1958 and to 1986. So 1958 is when the concept of perceptron came out, and 1986 was when backpropagation as an algorithm was put out. right? And we are here in 2019, still have to implement it, I guess. But why did it really take off now? I know
Big data,
on the right,
cloud and all that is what is kind of
yeah. So ability to process data has increased significantly, right? With big data tools, and then we have hardware. So unlike CPUs, now we have GPUs, right? And hopefully there will be quantum machines out soon. So the speed of processing has significantly increased, which allows us to train model on large data sets, right? And then needless to mention, we have cloud now, so we can put it out in cloud. And as a result of the first and second, there have been changes to the software itself. There have been a lot of new software which have been able to do parallelization, break it into smaller parts. So that all has helped. And then there has been development in the model itself, and there have been improvement in models as well. So those are the few reasons why deep learning or machine learning has really taken off. Okay. At its simplest level, if you break a deep learning, layers, or more so an individual layer, it's made up of perceptrons, right? It's made up of, if you have seen the notation, circle, individual circle within a layer is called perceptron, right? And so what I have here is, this is for intuition. I wanted to go to the most granular level and kind of talk about a few intuitions, and hopefully that kind of gets into you and it becomes easier for you when you go on your own, try to chart out the course of machine learning. I know many of you here want to do that. So if you were to imagine x1, x2 are the inputs to our model, or in this case perceptron, right? We have individual weights for them, which in this is represented W1, W2, and W3. So essentially, there are two steps in the model, primarily, right? The first step, which is linearity sum, or linear relation, right? What is a linear equation?
it will be XY and maybe Y is increasing, X will increase.
Right. Which is given by the equation, right? W1 x1 plus, in this case, W1 x1 plus W2 x2 plus W3 x3 plus bias, right? We learned it in our school days, linear equation, right? So the first function is doing a linear equation with each of the input and its corresponding weight and adding them all together. That's the first step, right? And then, the second step is what is called an activation or non-linear step, right? Which essentially is applying an activation function, which we'll talk about, and then the outputting an output from that perceptron, right? So if you think about perceptron, all it does is applies a linear equation, it sums it together, and then applies a non-linear activation to kind of give an output, right? So intuitively, what does it tell you? What is really happening? So for the different inputs, right, your weights, can be adjusted, right, which is giving its relative strength to each of the individual inputs to the output. That's the part of the linear equation, right? So if x1 has more, contribution to the output, you can imagine its weight to be substantially higher than, for the inputs x2 and x3, right? As a result, the linear equation would now be more aligned or more trending towards the X relationship, right? And the nonlinear activation essentially is needed because not all relationships are linear, right? And we'll talk about it. You will get more intuition as we talk through it. But to if you were to remember one thing, I think in a perceptron, remember this, that you do a linear sum and an activation function, right? For the people who are not going to really try to understand the depth of how it is really happening, and at a code level you're building Python, you probably don't need the depth of intuition or understanding of how exactly it's happening. At Python level, all you need to understand is I need to do a linear sum and an activation function.
So maybe for
Any questions? Yeah.
For the benefit of everybody, if we can throw in an example. So for example, like if you have to go from here to your home after the class, the traffic, the traffic on the road is your X parameter, but then all the other factors like signals, the density of the traffic are all your X2, X3, X4s. So, but the main parameter here is the traffic. So we are not going to reach home without either high traffic or low traffic, depending on what's the kind of traffic you have. But number of stops you are going to make may change based on the signals that you are going to get within the road. So imagine in that context. So there is one parameter which is actually holding it up for your output to be either this way or that way.
I have a question.
Sure.
I don't know if it's relevant or not. So, can we combine these linear function and non-linear function? Like, why do we have exactly? So it looks like we are solving a linear function, and then we are feeding the output to a non-linear function. So, what exactly we are achieving? Like intuitively.
So intuitively, if you think about it, right? If for sake of discussion, let's remove the non-linear activation out, right? So no matter how many layers you stack one after another, right, the net result could be still linear, right? Because you're applying linear equation. Now, when you do that, you're pretty much saying to your model, I think this is the relationship between your input to your output, which is linear relationship. What non-linear relationship allows you to do is, it doesn't, you are not putting out, to the model that you act only linearly, right? And we'll talk about it. I will show data points and how linear result is different, will be different than a non-linear output. Once I show it up on the screen, I think it will become much more easier to kind of relate to. But basic idea is that, right? If it's only linear, then you are inputting into the model that input is linearly related to output. And in most cases, like the one example he was describing and so many others, are not always linearly related to each other.
Can you give a quick use case now? A couple of years ago, AWS, they had a deep racer, which basically they let people program the deep racer, and so they also
What
had
did
a
they
race.
do?
Huh?
Say it again.
The deep racer, basically it's a car that you can program. So the car has to run through a circuit, and so basically the person who's programming has to take many factors into consideration: the speed, the curve of the circuit. So on I'm not sure if the curves are banked, but they would have to basically use the braking, the acceleration, everything has to be perfectly timed, so the car doesn't roll over. So they were capturing those data points and they were feeding it to the system, and the system was automatically trying to determine what was the optimal speed or what was the kind of turn it would have to make on those curves. So taking that into use case, how would you fit this in?
So that's a complex use case.
Okay,
Let me start from there.
Can you use something simple?
Yeah, and it's not just one model. Right now I'm talking about only one perceptron, right? Typically a model will have a layer, and within that layer there are many perceptrons, right? And then there are many layers, right? So if you were to imagine an image, that's easy to imagine, right? If you throw an image and all you want to detect is whether the image is of a cat or something else, right? You can imagine that the first layer, right, with the perceptrons, and let's say for the sake of discussion I have 5 layers, right? The first layer is trying to look at the image and find edges in the image, right? Where are the edges? Where is the body edge? Where is the face edge, and so on. The next layer will combine those edges together to form shapes. And as you traverse up in the layers, you end up building a much more composite representation towards the end, right? And finally, you kind of try to make a prediction based on the data which you have seen. So that's the intuition you should have. Model, the one which you described, that's not just one model. There are many models working together, feeding each other. That's a much more complex ecosystem. You raised your hand, sir.
Oh, I had a simple example.
Sure.
Assume Y is, you are a bank, you want to just give a loan. Give a loan or not give a loan is the Y. The X in this case, X1 would be like FICO score, maybe X2 would be your income, XM would be whatever, how much you put down. Feed that into that equation, transform it into a yes or no, and then the output is a yes or no. This is one layer or 0 layer. This is more like logistic regression. But when you start putting in some layers in between, then you have deep learning.
Okay. Awesome. Any more questions? Thank you. I'll briefly explain this activation functions, and if I don't get the intuition, that is fine. But wanted to talk about, because one of the important aspects of deep learning is applying linear and nonlinear functions, right? So within the nonlinear functions, there are many activation functions which we can use. What's up there is some of the common ones which are commonly used, right? On the left-hand side, what we have is sigmoid function, right? So in our perceptron, remember the output which was coming from the linear sum is fed into nonlinear activation. So let's assume that the linear sum is some value 100 and I should say 100. Let's assume that the 15 or 20 or whatever that number is, let's say 20. Right, so, and it is the input into our sigmoid function. So sigmoid function is essentially 1 by 1 plus e raised to minus c. It's going to output a value between 0 and 1, right? So essentially it's going to value a number, a probability between 0 and 1. So in the example you gave, it's going to give a probability whether that loan is going to pass or clear or not clear, in terms of percentage, right? 0.5, 0.6, whatever. So if you look here, the beauty of sigmoid function is, it's typically used for logistic regressions, typically used for classification problems, like the one described, right? Where whether you're getting a loan or not, right? It's not used for like a house price. If you were to predict price of the house based on the number of rooms, the area, zip code where it is, and a myriad of other inputs, right? That's not logistic. That's not a classification problem. That's a regression problem, right? So usually when you have a classification problem, sigmoid activation can be useful, and like I said, it gives an output between 0 and 1. And if you were to look at the sigmoid function, you will see that the slope is very steep, right, for values, right? Meaning, it's trying to push values either closer to 0 or 1, which is good for any model, which is essentially means either this is a cat or not a cat, right? Or the loan will be cleared or not cleared. Anyways, if you don't get the intuition, that is fine, and remember this, that these are the activation functions. These are used for applying a non-linear relationship with the linear output.
So would it be accurate? Yeah, so would it be accurate to say if that these functions are used basically to get the optimum value of whatever problem you're trying to solve? I mean, you could have different parameters, right? So it's possible that at one point, depending on what parameters you get, at one point that's the best possible outcome you can have with those parameters. And after that, it starts to die down. So would that be an accurate definition?
That's an important criteria, but not for this, right? We'll go through, as we go further, I think things will start getting connected. Right now, we are talking about individual concepts, and they will seem to come together. And if not, then we'll talk about it, how we can stitch it back, right? Go ahead.
So the rules of the function, the red is a slope. Is there a reason that we generally care about the slope? Or I'm sorry, the derivative?
It is, right. We care about slope for backward problem, right? When we are adjusting our gradient, which we have talked about, right? These, it's essential that, slope is steep, right? Because if you can imagine, one of the problem with sigmoid function is for higher or very lower values of x, right? Which you can imagine on the, the extreme top right side and, the closer beyond, the left bottom, right? It's kind of coming close to the axis. So it's basically ranging from 0 to 1, right? And that drop is steep, but once it is closer to 1 or 0, it is kind of, plateaued, right? It kind of goes at the same level. So if your weights, for whatever reasons, have been initialized such that, your output is somewhere there, right? Then gradient which you take, you won't be able to move because the gradient will be 0. That's the problem of vanishing gradients, which I don't intend to get here in this, but we can talk about it separately.
What is this red line?
Oh, the red line shows the distribution. Anyways, yeah. So similarly, so it's like sigmoid function, there's the tanh function, which again is it ranges from 1 to -1, again for non-linearity application, and is given by that equation. Finally, we have ReLU. ReLU is practically one of the most useful activation is ReLU. I should say most useful. It's one of the most popular activation which is used. So, in that ReLU, if you see the way it introduces non-linearity is, unless the value of x is greater than 0, it outputs 0. Right? So it takes a max between 0 and the value of x. Now, I'm not sure, whether you got intuition, but is there something why do you think ReLU will be better than sigmoid or tanh function? Is there any intuition?
It will give more accuracy, whether it is 0 or 1, whatever. Classification wise, we'll get more better output.
For the sigmoid function?
For the ReLU.
Okay.
And sigmoid, in cases where it could be maybe between somewhere, we still have very less accuracy whether it is 0 or 1.
Okay.
if your value is somewhere in between vaccine points. If it is in the end, maybe here and here, you know whether it is 0 or 1 or close to 0 or 1. But somewhere in the middle, you don't know it. So you still have to accuracy will be very less. That's what I think.
Okay. Yeah, good.
Well, based on the outcome, most of the time it could be the maximum of life in that case, so that's why it's more problem.
Okay. Okay. Yeah, that's true. The other thing, one of the key differences. So as I was saying earlier, activation function is attached to the output of linear function, right? So if activation function like sigmoid and tan h is always going to output something, right? It's going to output some number between 0 and 1, right? The versus value, right? Anytime it goes into negative, it will output 0. Now what happens because of that? If you were to imagine layers with lot of perceptrons, a few of the perceptrons will now get value 0, meaning it's shut off, meaning it's not being used for the output. So just to give you intuition, if the model is going through an image, right, and as you can imagine, 512 by 512 image will have the image in a specific area, but for most part of its pixels will be meaningless for the model to interpret anything, right? So in those cases, what would essentially happen is it will switch off those areas. So your computation becomes really significantly lower, and your model is able to work better with the data with which it is supposed to work with, right? So in that sense, value makes it much more effective. Anyways, What
question, sir? Can we have different activation function in a single layer?
So we didn't go there yet, but within every perceptron has ability to add a non-linear function.
And you can choose any one.
You can choose any one of those. Typically within a layer, you select the same non-linear activation, but you can have as many layers as you want. And so if generally sigmoid is kind of used towards the end or just before the final output. As you can imagine, it's classified between 0 and 1, whereas value is kind of most commonly used in the middle layers, right, which is outputting a value. Right. So yeah, answer to your question is yes.
Thank you.
So at a high level, can we see all these activation functions are for classification problems, not really for regression problems?
It is for regression as well. So irrespective of what problem you are trying to solve, remember this: between input and output, is there a linear relationship? In most cases, the input and output are not linearly related, right? Which is what I'll show you, right? So if you look at this data distribution here plotted on a graph, and if the X and Y are two classes, red and green are two different classes, right? And if you were to do a model without a non-linear activation, what will be your output? Right? Your model will probably give you this kind of line, right? Because it's linear, all it can do is a linear relationship line, right? It has no way to arrange itself. It has to arrange, it has to be a linear line, right? So one of the output may be this, which in no way makes data distribution, right? Once you introduce non-linearity, your model now has capability to kind of make those minor twists, adjustment, turns, and so on when it is, getting built, right? So non-linearity allows this model to take twists and turns. And it's able to now define boundary really well between the two classes. So I hope this gives you some intuition on why linearity and non-linearity is kind of plugged together. Pause here for a minute. Make sense? Does that help tie some of the discussion which we were having earlier? Okay, I think this is just for intuition purpose. As you can imagine, you can add more perceptrons and you can add more layers. Right, so let's see what we can talk through here. Right? So this is deep learning, right, or neural net. I shouldn't say deep learning, it's neural net. It has only 2 hidden layers in this case. And then we have an input layer and an output layer, right? So other than the linear relationship and non-linear activation, other intuition you should get is the W1 and W2 in this case, W1, W2 and W3 plays a very important role, right? It's the weights given to the input into each of the layer or 2 perceptron. So if you adjust weight for x1 in the first linkage, such that weight W1 for x1 is say 0.9, what would be its contribution to the output? So let me state this question again. So let's take only 1 perceptron, right, receiving 2 inputs x1 and x2 with weights W1 and W2, right? And W1 has a weight of 0.9, relative weight of 0.9, whereas W2 has relative weight of 0.1, right? So in terms of weightage, what's happening there?
X1 will have, of course, more.
X1 has now more say into the output, right? So by adjusting W1 and W2, you're kind of making the input which you're getting relevant to the output which is going out, right? So that's where you are kind of linking it together.
And initially, we don't know, what should be the ideal weight, right? So probably it's more of a random, we say, okay, so maybe 0.9 and 0.1, but later on, it will have more accurate kind of weights.
We will get there. That's a good intuition to have, right? Initially, we don't know. So his point is, I don't know what weight should I give them, right? So you start with setting up random weights for each of this layer, for each of this perceptrons, and kickstart your model from there, right? And we'll talk about how does the model learn, how does the model, over time change the value of weights to match the output it needs to produce.
Question?
Sure.
So the B1s are constants in each one of the layers?
B1 is biased, yeah.
Biased.
B1 is biased for each perceptron in the layer. It's not one for the layer, but each perceptron. Okay, so to go back to your question, like in this model, right, if you see the first layer or the first hidden layer has rel u as the activation function, right? So if you were to imagine if the output is lower than 0, then it's going to output 0. If it is higher than 0, it's going to output a number. If it's 0, that particular perceptron will be switched off, and its contribution to subsequent layer will not be there, right? And the last one in this case, where it is I think it should have been here, here on the, A3 is the sigmoid, right, which will output, I think, that has to be changed. It has, sigmoid is in your last layer, it is identifying the class for the classification. Okay, so far we have built perceptron, we have put our linear, non-linear equation. We also randomly set our weight, and we ran it for this data, right? And we had to predict for the red point, right? the problem we are trying to solve is for that data point, am I a banker or a software engineer? Yeah, we get paid less, I guess. Right? The model comes back with inaccurate results. So why do you think what needs to be done here? Why did the model predict incorrectly?
Is this a deep learning model?
It's a deep learning model, the model which we are building so far. Right, we built out, we had few layers, we initialized it with random weights, we ran this data through, but we now fed a new data point for which we don't know what label does it belong to, whether it's, for that data point, we don't know whether it's, it's an investment banker or a software engineer. Unfortunately, the model has come out with a wrong prediction.
And if they points at that place where it was,
Okay.
at the place where the sample was, there you go.
Okay, so we need enough data points with the same.
Yeah,
So
so
it's
that's
okay.
why we need to analyze the data, we need to map the data.
Okay, okay, fair point.
Yeah, but it could just be underfit.
Okay, sure, it can be underfit as well.
We need more dimensions, just not salary and wage, but probably more dimensions. And because of the value function,
Okay,
because if you ignore anything less than zero and if all the software engineering guys got, majority guys got less than zero and then
we get paid. We get underpaid, but we get
yeah, some of the things, maybe that is the reason.
Okay, okay. All those are good intuitions, I think. Yeah, go ahead.
Well, if you want a linear, you can go through that and it's going to get some of those points there.
Okay.
And it should not, because you can apply a linear function and some of those bankers and engineers are going to apply, so it depends on.
Sure, okay.
I have a quick question. In
Sure.
a scenario, if we know that like the right label and we try to tweak the model like changing weights, bias and some activation function, and we are able to predict this red dot correctly. So what does that mean? Like insufficient data or the wrong model parameter?
So, yeah, I think that's the question I was trying to ask. But yeah, I think you touched on few paradigms or few aspects of it. So, I think, yeah, you nailed it to a certain extent, right? So far we have built a model, but we didn't tell our model what's right and what's wrong, right? We haven't trained the model. We need to train our model. Of course, some of the things which you raised are important, right? Those play a role in the training as well. But in this case, the assumption was, which I didn't say in the beginning, that salary and age is sufficient for us to predict, right, which class they belong into. But the point here was, we initialized with random weights, right? Just by feeding data in, it's not going to be able to predict because this model right now is like a baby. It doesn't know what real world is like. So what you have to do is you have to train your model, right? So what is training, right? What do you mean by training?
With the known data points, you
We
understand.
need to build some rules for that.
Okay.
Well, come up with a model that filters the other ones.
It just weights and
So they wouldn't get the bankers, just the engineers. That's trial and error. So if you get it and filters the other one, then you would know that you got the right model. Trial.
Okay.
Iteration.
Okay.
To define the outcome.
Okay. What do you mean by defining the outcome? Sorry,
For example, let's say you, I can't think of a real life scenario, but let's take cars, right? So gas mileage. So gas mileage is subjective. Some people say, okay, I get 15 miles a gallon. It's great, sports car, 50 miles a gallon great. For some people, no, I need at least 45 miles a gallon. Go for a Prius. So basically, what's a good gas mileage, bad gas mileage, medium gas mileage? What kind of a car? Is the gas mileage good for a sports car? Is this gas mileage good for a regular passenger car? You know, so you're defining the outcome. So okay, for this kind of car, this gas mileage is good, or it's okay. So it's kind of lets the person who's looking at the data to make sense of what kind of car would be the right fit for certain kind of person, and depending on if they would be interested in that kind of car, and then you can market those cars for them.
Right. Yeah. I think in a certain way, that's the intuition, right? Where to keep it simple. Basically, model is going to predict some value, right? Now, what's the right value, right? So what you do is you compute what is called as a loss function, which essentially is difference between your value, which your predicted value, and the actual value, right? So what model needs to do is this difference has to reduce, right? It has to continuously come closer and closer such that the loss function value is minimum. Does that make sense? So if it's a house price, right, this is easier intuition, right? If my model says, hey, for this house, price should be the number, prices are going up in Dallas, different story, $225,000, right? But the actual price is $450,000. So now the loss function essentially is the difference between 450 and 225. I know I'm really 225 short here, right? So that's the loss function. That's the difference between the actual and predicted. And that is kind of fed back to, which we'll talk about in a backdrop, for the model to start adjusting its weight so that in its next cycle forward, it's going to predict a much closer value to 450. Right? Does that make sense? Intuitively,
Almost.
Okay.
But in order to have a prediction, you have to take, I think, a subset of the data, because can you run a prediction on your entire set of data and compare that to the actuals?
Yes, so in the training, that's what we do, right? So we have set of data, sample data, right, which can run in hundreds, thousands, millions even, right? And you have it labeled, right? And when you train the model, right, you're training the model to, and we'll talk about it. It's going to predict, and then we compute the loss function, and then traverse it back to the back propagation.
So he's trying to say, like, suppose if you have 100 data, row of data, you take 80 to build your model, 20 to test your model, test it, like you divide randomly, take the data out for the testing from the same data set.
That's a different concept, right?
That's what I'm talking about.
So
Test data versus model data.
Yeah, so we haven't reached there yet. So right now, we're talking about training that model. So for training the model, you have to give, the actuals, right? And allow the model to predict for every sample, right? And then, the forward pass, at the end of forward pass, you compute the loss, which I was describing, how further are you from the actual value. You adjust your weights in your backdrop, and then you come back again with the new values of weight to come up with a newer value and see how close you are. Right? So model, when it is trained, it's not only run on all the samples, but it is run multiple iterations. Right? So that's why processing needs are very high. Right? The compute processing needs are very high, and that's one of the big reasons why the models were out there since 1986 or whatever, right? They didn't really make it big until now, because there's no GPU, no cloud processing power to have that kind of capacity to process data. Go ahead.
So the use case that you just described, this is based on historical data. that is the real estate prices. Now, there's a factor that determines the cost of the home, that is market conditions. So market conditions will change in future. So all the training that you've done on your model has been based on historical data. But how would you predict a home price in future? Because that's because your model is now trained on historical data, but you need some other information which will help the model to predict the price of the home in future.
There is something called the home price index that's forecasted. It's an index. Home price index HPI will be forecasted also. So it's an economical variable that will forecast that the economy will be, that number will be that much. It can be GDP and other macroeconomic variables. Yeah, so it seems it's a factor.
So what we are talking about is a very simplistic model where we have based on the certain attributes of the house itself, we are trying to forecast the price of the house. Like that person said, there are other factors which will play in, right? When you think about future prices, exactly to your point, GDP, market might have gone under recession. So many other factors will come into play. Right? Those will be data points which will supply into the model for it to be able to, factor in those attributes in its prediction. Right. But what I wanted to do here is kind of give an intuition of what loss means and how is it relevant and why our model wouldn't have predicted properly unless it factors in the loss. Right. We are okay. So cost functions again, just like activation functions. I think it's in the next slide. But like I said, loss function is essentially a difference between your predicted and actual value. And what you do is you calculate the loss over the entire sample, right? And that's called cost function. So loss function is at an individual, sample level, right? Whereas cost function is for the batch of samples.
But do we know which activation function we have used, like sigma or damage? Looking at this, we don't know, right?
For the loss function, no, it doesn't really matter. All that loss function tries to compute is what do you predict, what is the actual, right, and what is the difference between these two, right? And we'll talk about how the corrections happen. Okay, so briefly to touch base on cost functions or loss functions, there are again quite a few. So I just put out two here. Right? Definitely there are many others. So mean square error loss is typically used for the regression problem, like the house price. Like I was saying, if it's a continuous output, right? House price is not a classification problem. It's a continuous output, right? So typically you would use a mean square error loss, and that is given by that formula, which essentially is difference between actual and predicted, and you take a square of it just to amplify the difference between those 2 points, and then you sum it over the entire sample. What we have, the second loss function which I have there is the cross entropy error loss. This is mostly used for your classification. So within classification, you can have many types of classification. You can be looking for whether it's a cat or not. It's a binary classification. You can be looking for whether it's cat or dog or giraffe, right? So you can be looking for multi-label classification. And then the third category is multi-class, meaning within the same picture itself you may have more than one type, right? So irrespective, you can use cross entropy, and that happens to be much popular for classification. Anyways, if you are interested to know more about cross entropy, please feel free to read. That's something we'll not get into. But the intuition is this, right? Like I said earlier, we need to find out the weight star, right? For minimum loss function, meaning you make your loss as small as possible, and at the point where the loss is really the smallest, that's the best output your model can produce, right? In terms of weight values, right? That's the weight value, right? So the goal of the model is you go forward, predict, and compute cost. That cost has to be really low. So yeah, pause before I go any further. Any questions here?
So is this model work on the real-time scenario as well? So when I say the real-time, like for the smart car, when we drive it, so the results like this is the tree, this is the car in front of you, and the distance between the car and so on.
Sure, it will. Right now our model is not ready.
Okay.
Right? Our model, we have built it, it's able to take data and it is giving us value. We are talking about how do we train the model, right? Because from the, what it is predicting, like we saw earlier, right? It predicted, incorrectly, right? The house price was predicted 225, whereas the actual was 450, right? We want it to be as close as to 450. So we want to train that model before even we can put it out and someone can ask, hey, how much would my house price cost for model to respond? Right. So model right now is a baby and we are training it to understand data and predict accurately. Does that make sense? Okay. Okay. So that kind of gets into gradient descent, right? So this graph which you are looking up there, right, is the curvy thing which you see up there is the cost function, right? So this, if you can picture this, right, for different weights of W1 and W2, values of W1 and W2, the cost value is different, meaning, it's either close or further away from the actual value, right? So in this case, what wanted to kind of help you in picturing is, the cost value will not be a linear relationship again. Like in this graph, right? There are points where it's going into a valley, right? So there is what we say is there is a local minima and a global minima. Global minima is the lowest point on the cost function, which is where you want to get to. But there may be many low points in the cost function, and you may get stuck there. That's a different discussion. But the intuition I wanted to give here is you start with random weights, right? Like we said, in the forward pass, we give a random weight, right? Initialize our perceptrons with random weight. Do the forward pass, which is summation and non-linear activation, right? Then you compute loss. The loss function. If it's a regression problem, we are using mean square error or MSE cost function. We are computing the cost. Now, what we do is we take a small step towards reducing the cost and go back and adjust our weight. And we keep on doing this until we reach to a point where the cost function is lowest. When the cost function is lowest, when we are at that point, as it shows here in the picture, right, that's the point when my model, is best performed. I haven't talked about how do we do gradient descent, but does this help with the intuition?
Yeah.
Go ahead.
So that process, when you say, in your sentences, you're saying you or the individual, are there libraries that automatically adjust the weights for you so that you don't have to kind of manually switch the weights around?
So libraries do this for you, right? So the gradient descent is taken care by, Keras or Theano, or, so all you have to do is tell which cost function we use, right? So library takes care of doing the derivatives, right? But if you want to get a real good feeling of what machine learning is, then I recommend, write those by hand. Because once you implement this, functions by hand, you really understand what's happening under the hood. But there are a lot of libraries, which kind of abstracts many of these concepts away from you. I think in the interest of time, I move forward, right? I wanted to draw some kind of diagram. I ended up writing it here, taking a picture. So backdrop is all about, going down the slope, right? So how do you compute slope?
First derivative.
Right. Say it again.
First derivative.
First derivative, yeah. So if you remember from your algebra, y2 minus y1 by x2 minus x1, which essentially is, right, m equal to, slope equal to y2 minus y1 by x2 minus x1, which essentially is, small step in y with respect to small step in x, which is a derivative function, right? So backdrop essentially is you want to calculate, with derivative of loss with respect to derivative of your weights. So in this case, I want to calculate derivative of my final loss. We talked about how we compute loss, right? So derivative of that loss with respect to derivative of weight one, right? And how do you do that? In derivatives, you basically have a chain rule. All you have to do is calculate local derivative, and you kind of, multiply with each other, which gives you, derivative with respect to weight. So in this case, what you have to do essentially is you have to do a derivative of loss function with respect to, dy. Then the loss function, I have it there, right? And then, I'm not sure, I probably should write on a paper, but this is what you need to compute, dl by dw1, the derivative of loss with respect to weight one. So what does this do? So when you come back, what it is essentially telling is, by making a small change in W1, how much am I moving my loss, right? I'm calculating that, and then making that change to my previous weight, right? So I started with random rate, I calculated this loss, I did a derivative to understand how much can I tweak W1 to make a change in loss, and then change my W1 to move in that direction, right? And I keep on doing it iteratively until I come close, until my loss is very low.
So if you reach multiple optimum values like what we saw in previous then which one to pick? The right way to pick?
There are certain parameter tuning which we'll not get into today, right? You can tune your model in a way that you try to avoid getting it into local minima. So his question is basically, he showed me that diagram, there were multiple local minimas. If I get stuck in those minimas, I'll probably not come out at all, right? There are certain tuning which you can do. In addition, what it has been found is local minimas, although in theory it seems to have a big impact, but practically it doesn't really have as big of an impact on the model prediction. Any questions here?
Can we get these slides?
Sure. Yes. So all I have here is backpropagation for a single perceptron, Right now, imagine, as we add many perceptrons within a layer and many layers, and as they diverge and converge, right, you will have to basically backwalk your derivatives all the way to the input vectors, right? But chain rule makes it much simpler because you do it at individual layer level, and all you have to do is multiply between them. Okay. Right.
Like in case of different layers and like 1,000 over a million of neurons, perceptrons, sorry, and the weight is changed only for the whole layer. Like say from one layer to other layer there are X number of inputs. So the weight is same for, weight is different for every input.
Weight is different for every layer, right?
Every layer and every output of the layer.
Every layer input.
Every layer input, okay.
Yeah.
So that scenario, single cost function basically drives the weight for every input.
The idea is this, right? So if in fact, we are not trying to find out gradient for every W's, every weights,
Okay.
but we are trying to find gradient just for the input gradient W, with respect to the loss. Because the moment I change the input weight, automatically as I move forward in the forward prep, right, the W's in between, in the hidden layers, will get adjusted accordingly. Right, so that's the intuition. That's a good question. You don't apply gradient at every level. Okay. Are we running over time? Okay. Let me see. So far I think, so far where we have reached is we have taken a model, right? We built it, we have trained it with backprop. We have got cost function which is low, right? We know how to kind of continuously iterate to get to a low cost function. So the content which I have in the front is basically now, there are certain optimization which we can do, which would help save on the compute power which gets used, right? Like the gradient descent, I think one of the questions which you were asking, hey, do I run it over the whole batch size? My entire sample for the gradient, there are different ways you can do it. So it's an interest of time. Should I call it a day here? I see a lot of head shaking. Keep going. You guys are okay? Okay. Let me do as fast as I can. So these are three commonly used types of gradients. Batch, stochastic, and mini batch. So batch essentially is, with every iteration you run the entire set of samples, calculate your gradient, right? And then apply that gradient before you run the batch all over again. So if you have 1 million samples of data, right, you run the entire million forward prop, right, calculate the back prop, but apply it at the end of the million sample run. That's batch. So as you can imagine, gradient application is going to be very slow because you're going to run over 1 million samples. But at the same time, your gradient will be kind of smooth because you're doing it over the entire sample. I'll explain why it will be smooth. You'll get to know with the second example, right? The second way of doing it is stochastic, right? Which is the other way around. In stochastic, what you do is you run a single sample, backprop, calculate gradient, apply the gradient, run the second sample, right? So what does that do? You are applying gradient with every forward prop. As you can imagine, if there is an outlier data somewhere, my gradient with the loss function will be quite huge, and I may be going in a different trajectory. So it's the gradient descent is not smooth. right? It's zigzag, right? Because you're doing it on an individual sample, and individual sample may not be proper representation of the entire sample, right? So that's stochastic. Finally, the one which is commonly used is mini batch, where it's, as the name suggests, it's not stochastic. It doesn't do for a single sample. You can batch up, maybe if it's a million record, do it for every 50,000 or 100,000 samples. So you run it for 100,000 samples, calculate it, apply it, and then run it for the next 100,000 samples. So those are a few things to consider when you're training your model. Then the other thing which you need to think about is overfitting or underfitting, right? So what is underfitting? Underfitting is when your model doesn't really fit your data. Essentially means you have not really trained it well. You need to train your model not at the level it needs to be. You need to add more layers to it or whatever. The overfitting is where most of the issues are, right? Because model, the deep learning models, they learn from data, right? They learn from representation of data really well. So if you supply enough data, it will be able to predict accurately for your training set, right? So what we typically do to find out whether it's underfitting or overfitting, what we do is in case if we have like Krishna talked about earlier, in case if we have a sample size of 1 million, I may keep 10,000 sample aside. I train the model and then I try with my 10,000 sample and I see what's my accuracy rate with the sample versus my training set. Right? If my training set is 99% very much accurate compared to my test set where the accuracy drops to 80%, what it tells is basically our model is overfitting to training data, right? So there are certain techniques which you apply to ensure that there is no, you don't have a problem of overfitting, and that's called regularization.
So basically, if one model is idle fit and you bring more data, it becomes underfit. Same case like if you have a model and it is overfitting, as of now, you discard it and then you bring more data which you don't have label for, and the model which was idly fitted, now it is underfitted, but the model which was overfit earlier becomes idle fit. So do we see these kind of scenarios in real?
Oh, model training takes a lot of time. So you go between, you don't go that frequently between overfitting and underfitting. But it takes a lot of time to train model, right?
Also, the case you are talking about, there may be data outliers where you are seeing so much of variation. Whereas, if your sample sizes are such that you don't see that much of variation in real life.
Yeah, what was the assumption of my question is that you have a model which is like giving you 90% accuracy, whatever bit you are following, and after some time it starts giving it you 80% or 70%. But anyway, let's carry on.
Oh, the same model drops in accuracy?
Yeah,
that happens all the time. So,
but then the overfitted model that you discarded earlier becomes the idle fit now.
yeah, so the model building is not something you do it once and keep it aside. You have to frequently check the accuracy of model, right? You have to frequently tune the model. Right? There are many parameters which you can tune, right? So it's an ongoing activity. It's not a one-time activity. But yeah, that frequently happens. So regularization, so regularization essentially is a technique where, like I said, the model, you want to make sure that model is not too tied to the training sample. So you kind of introduce a little bit of uncertainty or error in model training. So model is now finding it difficult to kind of, predict or depend on one certain element for its prediction, right? One of the common technique which we use today is dropout technique. So essentially what you can do in dropout technique is you can turn off certain percentage of percentrons, right, randomly. So while you're training, you can imagine the first sample maybe Z12 and Z14 in this picture has been turned off, right? So model is actually using only 2 perceptrons in the layer 1, whereas for the fifth sample, it may be the first and the second and the next 2 are turned off, right? So you keep switching off perceptrons as the model is training, so that model doesn't get dependent on only one perceptron for its output. So this is one of the popular regularization techniques which we employ. It's called dropout. The another one, there are more regularization techniques. I just threw a couple just to give you guys an intuition. This one here is called early stopping. So what we essentially do here is we plot graph. So the green one in this case is training data, right? So like I was saying, your testing sample, you distribute it in a training set and test set, right? You train your model against training set. So it's training iteratively against the training set. It's improving itself, and finally you have, the accuracy, which is now plotted here in this case, where you're plotting accuracy with, or rather loss with, the number of iterations you're training your model. And as you are running the number of iterations, what you do at the end of training, you also feed in the test set, right? So this set is which model has not seen at all during its iterative training. So this is the first time it is seeing that value, just like anyone, as if anyone is using the model, right? And then, get its output and see what's the loss. So then we track, right? So here in the plot, it kind of shows between the difference between the training and testing set. So if, so as you can see, at a certain point, the training set is kind of becoming better and better, but testing set is degrading in performance, right? So you want your model to stop at a point where testing set is about to degrade, or around the point where it is degrading, right? So you can do that by having early stopping. That's one of the regularization techniques as well to prevent overfitting. I think that's all I had for the content today.
Question?
Sure.
So most of these show the loss sort of asymptotic to zero, but for practical purposes, is there kind of like a rule of thumb or just kind of accepted good practice, right? Where when the loss gets below X percentage, the model's probably okay. It could be 10%, 20%, 30%. Is there anything like that you've seen in practice?
Oh, for the accuracy? Yes. It depends on the use case which you're trying to solve.
Right.
So
So
for example,
probably not.
So if you are showing a recommendation, like for Neiman Marcus, if you were to throw on our website a recommendation, when you visit our website, right, based on whatever criteria, right? The accuracy is needed, but I don't need 100% accuracy. If I can get to that, that's good. Even if I can throw out by 90% accuracy, awesome. Right? On the other hand, like you said, if it's a medical or if it's a car driving on the street, you want it to be the 100% or close to 100% accuracy, right? So it depends on what use case you're trying to solve.
What is your current accuracy?
So the accuracy also, like I said, right, it keeps on changing, right? And that is one thing which we have to keep on doing, which I think he was asking, right? You go out with 98% accuracy, you get new data, and you find out your accuracy has dropped, and then you kind of have to retune your model, or tune your type of parameter, and so on. So it's always the cat and mouse thing.
Can we, just a hypothetical question, can we have randomly generated data which is similar to the original data, but which you can see in foreseeable future, and have your model trained on it and have a model ready, rather than retraining it when you see the new data, you already generated a sample of data which is similar enough, not the same, but you see like if you can, you get what I'm saying?
Yeah. There are models out there. So generative adversarial network, which is gone. They generate data, but based on sample distribution data. Application, I think the recent one which really took off was, I think it's called My Face app or whatever. Where you can take a picture and it shows you when you're old, right? So all of those use generative under the hood, where it generates, image. And yes, that's one of the areas which is really taken
But
off.
it generates based on the current distribution.
Current distribution of data.
Okay.
Right, so it generates based on that, and that's really taking off, because like you said, if I'm able to generate data on my own, I don't really have to go out and try to sample data, right, or create my own samples of data. Awesome, good. Thank you, everyone.
One quick question. How many people would like to see a sample running code on certain data?
Good.
After, because we went to theory class, do you want to see a practical lab for this?
Yeah, so if you have like visualization, if it's like in MATLAB or
It's
something.
all there. It's all there.
Yeah.
So, last time we did the ski learn Lijesh did it on number classification to show how it's done. Also calculate loss function and all this what we talked. And also we also did it on the keyless TensorFlow and keyless to show how this value and every all functions and everything. And we also did it on AutoML for the Google. So if you want to see that and just the feedback, we decide what other people want to see.
Yeah, I think that's good. This we brought up. We should probably have asked this early. So one thing we are trying to figure out what interests you more, right? Is it the intuitions which we talk about, or is it the code which you want to see, right? Because we were doing code, we used to show codes in our earlier session, talk about a model and run it through here. But then we had, like I said, the last session was all about intuition of vector spaces, and I saw a lot of people getting really excited about it. So that's why we decided let's do intuition on the deep learning. But I think it's trying to ask which one do you prefer?
My suggestion would be probably 4 out of 5 is more the intuition, and maybe 1 out of 5 is on the actual coding, because like configuring machine, everybody has a slightly different laptop or slightly different download, and like all that stuff eats away at like the real learning. And it's just more administrative.
Okay. Yeah, I hear you. I think that's a good idea.
I have a kind of request regarding that. Please do some example which is like not generally taken. Like in case of deep learning, we have that image recognition thing. Tutorials are all over the internet. So do like something which is not out there, some kind of problem which is not frequently given an example of application of deep learning.
Okay. So you want on the more frontiers of machine learning?
That would be great if you can do that.
Yeah, I think the challenge is you can talk about frontiers, but you won't be able to relate unless you have intuition of the basic fundamentals. Which is true if in my mind it kind of boils down to what is audience's interest overall. That's a good call out. Maybe we should plan one on such kind of specific topics. Nice, awesome. Again, thank you. Thanks everyone for coming in.
Thank you.
Sorry, my bad. All this was possible because of our partner here, right? And Convergence is our partner. They have gracefully given this location to us, and the food which is out there has been provided by them. Thank you, thanks Dustin and team, and to make it really happen.
Dustin, you want to have a word about Convergence?
Yeah, so Convergence, this is my recruiter here actually in this building, on the second floor, is where our Addison location is. And actually, we replaced Kip at GM Financial. Brian did, yeah. And then some of our other clients, Capital One, Neiman Marcus, obviously GM Financial. So we have several clients around here in DFW. Typically, we have some machine learning, artificial intelligence type roles. Right now, we're a little light on those, but I told the guys earlier that we just found out this week that we have over 200 developers at Capital One, if anyone is in the Java, AWS, in that realm. So, you guys know anyone?
Yes, I know there's many people.
Perfect. But yeah, we have a bunch of cars over here, so I'd love to, if anyone